Okay, so now we're going to do a bit of implicit differentiation. Okay, differentiation. Okay, so the first thing that we're going to start off with is by saying that if f of xyz, if this multivariable function is equal to 0, then that means, and this is kind of a big leap, but that means that z, our z component, could be a function, z of xy, where x and y are independent variables. X and y are independent variables. Okay, so what I mean by that is that our function is actually xy and then a z of xy. So our height depends on that x and y for it to equal 0, because then that means that instead of x, y, and z being like completely 3 independent variables, now we only have 2 independent variables, and the third one kind of accommodates, or it kind of accommodates or adjusts for the x and y, for the changes in the x and y, in order for our function, our entire function, to be a constant at 0. Okay, so anyways, this is kind of like, just a little side note, this is kind of like when we had something like f of xy. When our multivariable function of 2 variables is equal to 0, then x is independent, and our y is a function of x, because it has to adjust, right? But anyway, so that was just a little side note. Woo, moving the screen. Okay, so that was just a little side note there in the middle. Now we'll just move on. And so anyway, so that's what we're starting with, is that f of xyz is equal to 0. Okay, so what we actually have is something like I was saying here. So this f of xy z is equal to 0, right? So now we have f of x comma y comma z of x and y, okay, because z depends on x and y. So this is kind of like a composite function, right? We have our x, our y, and our z, and our x and y, they're just themselves, right? X is x and y is y, so that's not a big deal. But then z is a function of x and y, so that makes it a little bit more complicated. So we'll see how on the next slide. So we're starting with this function of x, y, which are independent variables, and then z, which is dependent on our x and y. Okay, so x is equal to x, simply, y is equal to y, and z is equal to z of x and y. Okay, so let's say we were to differentiate x. We're going to take the partial derivative of f with respect to x. Okay, and if we were to do that, the chain rule would tell us that we're supposed to take the partials, take the primary derivatives, right? So this x here is not the same as the x here. The x here represents like the position that it's in, so the first position, the first component, right? And then our dx, x, we have another x because it happens to be the same. Okay, so for the next term we would have the primary derivative, partial f, partial y, and here this y represents the second component. Not exactly, we could have something else written here like a t or a z or something, or any other letter, but that just represents what's in the second spot there. Okay, and then we have partial y, partial x, okay, because that's what we're differentiating with respect to. And then our final term is going to be partial f, partial z, okay, so now we're referring to the third component, and then partial z, partial x, okay? And we know that since our original function equals 0, the derivative should also equal 0, right? That's just going to be a 0. And what we can do here with this equation is actually a couple things. So we see here that we have a dx over dx, or partial x over partial x, which is equal to 1, right? Okay, so that's equal to a 1. And then this term here, if we look carefully at this one, we see partial y, partial x. So how much is y changing with respect to x? It will not at all. There is no relation between them because they're independent variables, right? We start off by saying that x and y are independent, so that means that this term is 0. So this whole middle term goes away, all right? So what we're left with is a partial f, partial x times 1, plus partial f, partial z, and then partial z, partial x is equal to 0, okay? So I'm just going to rewrite these in a little easier or simpler notation. So partial f with respect to x plus partial f partial z, and then our dz dx there is equal to 0. So if we were to solve for this, solve for our the relation between z and x, we would get that we have a negative, so this would be a negative f sub x over f sub z. Okay? So this is actually a pretty important relation that we just uncovered. It's kind of like a shortcut that we can use the primary derivatives. So f, our outer function with respect to the first position, and then f with respect to the partial derivative of f with respect to the third position there, whatever's there. We can take that and kind of just plug it into this formula in order to find the relation between our z function and then the x there. Okay, so we just found how is z related to x. Okay, and similarly, let's say we start over. So we're starting with our f of x, y, and then z of x, y, and then we're going to say it equals 0. And then x, again, that just equals x, y is equal to y, and z is equal to a z of x, y. So that's a function of x and y. And again, x and y are independent variables. Let's say we were to go through and take the partial of f with respect to y this time. Okay, so in this sense, what we would get is partial f, partial x, partial y, plus partial f, partial y, and again y meaning our second component, not the y itself, and this one's partial y, and our last one's going to be partial f, partial z, partial y. Okay, and this again equals 0 because our original function equaled 0. So when you differentiate the original function, which is already a constant, then it just stays 0. Okay, so here we see this one is partial x, partial y, and that is going to turn out to be 0 because the variables are independent. Those two are. And then here we see a partial y over partial y. So that's going to cancel out to be a 1. Okay, so we simplified that, and what we get is partial f, partial y, plus partial f, partial z, partial y is equal to 0. So if we rewrite that a little bit, we get f sub y plus f sub z times partial z, partial y is equal to 0, and then we get that partial z, partial y ends up being a negative f sub y over f sub z. So here again we see one of those useful relationships between the partial derivatives, in this case the primary derivatives, right? So here we can kind of see that if you want to discover the partial of z with respect to either of the variables, x or y in this case, then you basically just take the primary derivatives of your original function with respect to each of those variables, you stick the other one on top. So see how it's kind of flipped, like with the y's are across from each other and the z's are across from each other, and you add a minus sign in the front there. So anyways, these are just kind of like shortcuts, right? So again, our conclusions for those last couple of things was that partial z, partial x could be found by taking the primary derivative with respect to x and sticking it over the primary derivative with respect to z. And that last one was if you want to find the relation between z and y, then you would take a negative of the partial of y over the partial of the original function with respect to z. Okay? So that's pretty much it. Those are our little shortcuts at the end there. That wraps it up for the chain rule, and I hope that helps, and good luck on your homework.